Welcome back. So this time we want to try to answer this question. A ball rolling horizontally off a 10-meter tall cliff. It's initially rolling horizontally at 3 meters per second. And we want to find out how far away from the cliff it'll land, which means this distance. How far away, because the ball is going to do something like we talked about in the last video, like this, in terms of its path. And we also want to find out at what speed, what velocity, meaning speed and direction, the ball is going to hit the ground. So this is actually a pretty complicated problem, but it culminates in everything, almost everything we've done all year long. The way to do this, the way to go about these types of problems is to, and you should still have your notes out, separate your vertical and horizontal. We've done free fall, and we've done stuff that isn't accelerating. For vertical piece, this is nothing more than the free fall stuff. For the horizontal, this is acceleration equals 0 meters per second squared. So we want to separate these two, and then only at the end do we put them back together to find our final v. So our direction is going to be something like that. So we need a magnitude and an angle in order to properly identify what the final velocity is. And then once we know that, well, actually separately, we'll be able to figure out how far away from the base of the cliff, from here to here, it's called. By the way, how far from the base of the cliff? This is also called the range of the ball. So, excuse me. We're going to take this piece by piece. The first piece is looking at the horizontal and vertical. When you set up these problems, it really helps to make a table. This table should be separated into vertical pieces, that's this V, and horizontal pieces, information, the horizontal. Everything we know can be figured out into either vertical or horizontal because everything we're going to be looking at is a vector. So the direction matters. If it's an up-down piece of direction, it falls under our vertical. If it's a left-right, it falls in our horizontal. There are things we know, and there's only one thing that you should ever allow to cross this line. That one thing only, is the following. It is the only scalar we're going to work with, and it's time. We're going to have to find the time, but time is the only value that I allow to cross this bridge being this vertical line. Everything else is completely separate. We deal with these, it's almost as if it's two separate problems at the same time. So let's start just identifying some of our knowns. This 3 meters per second, going along with the last video where it's as if gravity were turned off, this ball is always traveling horizontally at 3 meters per second. So our VI is 3 meters per second. Just like in the last video also, as soon as the ball leaves the cliff, as soon as it does, its vertical piece, it's almost as if it were just dropped. Because gravity doesn't really care from the last video that it's going 3 meters per second. It cares only that it wasn't thrown upwards, nor was it thrown downwards. So our VI here is 0 meters per second. But that gets a little tricky. So how do we deal with it? We have to add an extra piece of information. And I'm going to rewrite this. Our VI is going to be rewritten not just simply as VI, but we're going to add an extra piece of information. Just like with math, where vertical is the y-axis and horizontal is the x-axis, so we're going to call this VIY for the vertical, meaning the initial vertical velocity, and VIX for the initial horizontal velocity. Completely separate values, completely independent of each other. They don't mean anything to each other. They don't even know they exist. But other pieces of information do correlate to each of these. In order to find the speed or the velocity when it hits the ground, we're going to be looking for VF in the same fashion, VFY. That's what we're first going to be looking for. That's part A. We know that the acceleration is g, negative 9.81 meters per second squared. We also know that d is negative 10 meters. Negative because the ball's getting lower. Remember, these negatives really mean something. So we have g, which is really our acceleration, our vertical acceleration. We are looking for VFY, we have VIY, and we are looking for time. Time is the only thing that means both in terms of vertical and horizontal. It's the same time, the ball that goes here and lands down. Horizontally, VFX isn't going to change. There is no horizontal acceleration. The ball doesn't feel any effects because we're ignoring air friction just like we always do. We're going to be looking for our dx, really this should be dy. We're going to be looking for our dx, that's our horizontal range. Our time is still the same, and just for completeness we're going to write that our horizontal acceleration is 0 meters per second squared. It is not speeding up. So let's tackle this first problem first. I already know VFX. We're going to have to do some trig, just like we've been doing in the past week. But first, we have to find VFY, because our final velocity is going to come from a combination of VFX, which will just be the 3 meters per second squared, and our VFY as our other piece, because this one's purely to the left-right, this one's purely up-down, so our resultant is really our full and final VF. So this is where that trig piece comes in. So we're going to have to find not only VF, but also that angle at which it is, because velocity itself is a vector. Okay, so how do we do that? Well, finding VFY, we only care about the vertical piece. That's the only part we care about. So let's find VFY. Well, VFY, looking at what we know, we have VFY, VIY, A, and D. We don't know T, so we don't need that. But we have an equation, VF squared, so VFY squared, all the equations that we know and love, is exactly the same. VFY squared equals VIY squared plus 2AY dy. Just add those subscripts into these equations. So, our VFY squared, what we're looking for. VIY squared, well that's 0. Plus 2, our AY, negative 9.81. Our dy, negative 10. That means that VFY squared equals, check my notes here, 196.2. Since we have this squared term up here, we've got to get rid of it by square rooting both sides, which gives us VFY equals 14.01. You should be checking, you can check this in your calculator, meters per second. But because the ball's ending down, it's falling downward, this really is plus or minus. But since it's ending downward, it's not plus. Upwards would mean plus, downward, since it's falling down, we get our minus sign. So we can now fill this in to our VFY squared and get our final answer for our VFY of negative 14.01 meters per second. Okay. Next, we're not done. We have to take our VFY and our VFX and combine them to find VF overall. So to do that, I'm going to erase all of this. So hopefully you're taking down these notes, so you'll have to still see these. This is going to go away as well. So if the sub needs to pause, now's a good time to make sure that the students have this copied down, because it is going to go away in a second. So we're going to be looking for VF using our VFX and VFY in order to find our VF, you're just using Pythagorean theorem. So here we go. Reminder that VFX is 3 meters per second. VFY we just found to be negative 14.01 meters per second. So we draw our triangle, 3 roughly to scale, doesn't have to be perfect. 14.01, really you shouldn't have this negative here because the arrow takes care of that negative. And our resultant is this one. That resultant is our V final. Using Pythagorean theorem, V final is the square root of 3 squared plus 14.01 squared. Gives us a V final of 14.33 meters per second. But we're not done. Now, that's only our speed. Velocity is speed with a direction. So we need to find the angle. And the angle, which is this part right here, comes about from our inverse tangent function, just from last week, of the opposite side of the triangle, which is our 14.01, because it's opposite of this angle, divided by our adjacent side, which is a 3. So 14.01 over 3. That's not a negative. Which, when you do in your calculator, you get 77.91 degrees. So, this part, combining our speed and our direction, gives us a final answer of V final equals 14.33 meters per second at 77.91 degrees. Now the direction is a little bit tricky because we're no longer talking about south. Really, if you're on a cliff, it's falling downward. But saying down of east kind of doesn't make sense, so it actually gets a lot easier. When you have it set up this way, where the horizontal, the x part is on the top, all that happens is this would become below the horizontal, or below the horizon. I'm probably writing on top of my face, but this is really just below the horizontal. So here is our final answer just for the final velocity. Takes a little while to explain. As you get more and more into it, it'll get faster. In the next video, and I know you're like, oh, why are there so many videos? It's because I want to make sure that things are going smoothly and taking things slow. These are posted on YouTube, so if you need to go back to them tonight to work on this worksheet as your homework, which I will check tomorrow, on Wednesday, you should go back and look at these, because these will help you. So on the next video, which will be a short video, we're going to take our information that we have and figure out how far away from the base the ball will land. Thank you.